In this review session, we'll be looking at some paper 1 questions. The first one that we've got says, for which quantity is the magnitude a reasonable estimate? So we're looking at the frequency of a radio wave, the mass of an atom, the Young modulus of a metal, and the wavelength of green light. Well, I'm familiar enough with this because it just so happens that my favorite color is 510 nanometers. That's a particular shade of green that is my favorite color. 509 nanometers, 511 nanometers are just not quite right. But 510, that's the shade of green that is sort of my favorite. Like this is too light right here. It's a little bit darker than that. So I would just go right to D. I say, well, yeah, that's right. Green light's 500 nanometers. So let's maybe use this question as an opportunity to sort of disprove these other ones and say, well, these must be very wrong. Otherwise, it has to be very clear that that's the case. You could perhaps tie this back to the learning objective stating the wavelengths of the principal radiations of the EM spectrum. So it's good to sort of know that visible light is between 400 and 700 nanometers long. And so this goes from violet light, the shortest wavelength light, purple light, all the way up to red light, which is the longest wavelength. And you say like, oh, 500 is sort of right in the middle there. So green. So that's a reasonable estimate. Picohertz is the way you'd sort of read this and say, well, a radio wave, those are the longest wavelengths of light. And so they're going to have the lowest frequencies. Okay. The lowest frequencies. Here we have 500 pico. Pico is 10 to the minus 12. So let's maybe calculate the wavelength from this, because that's a nice little review too. So let's calculate the wavelength of this and say, well, is it in like the radio part? If your learning objective was to state the wavelength of the principal radiations, radio is a principal radiation, right? So you should know what the wavelengths of radio waves are. Radio waves are greater than, basically anything greater than what, 10 centimeters, something like that. So microwaves are like short radio waves, right? That's why they're micro. They're okay, short radio waves. And then infrared is just sort of just a little bit longer than red, right? So we kind of say, well, this would be 7 by 10 to the negative 7 meters. And so, red light would be just a little bit longer than that. So 8 by 10 to the negative 7, down to like 10 to the negative 5. And then you have things that are just, a few centimeters, the microwave part of the spectrum, and then the longest, all the way up to as long as they could be, greater than 1 million, meters or something. All right, so let's calculate this based on the speed of light. It's equal to wavelength times frequency. We can approximate the speed of light as 3 by 10 to the 8 meters per second. And if we divide that by the frequency given, 500 pico, 10 to the negative 12 hertz are reciprocal seconds. And so those units cancel. You got 3 by 10 to the 8 divided by 500 by 10 to the negative 12. What does that work out to be? Six by 10 to the 17 meters. So if there was a wave with that length, which I think this is like 17 meters. So how big is that? It's about the size of the galaxy. So I think our whole galaxy, 10 to the 22. So it's a good chunk of the galaxy, bigger than our solar system. Okay, so if there's a wavelength that long, yeah, it would be a radio wave, but I guess not a reasonable estimate because it's just so long. So it's like, well, technically a radio wave, not the best answer because this one clearly is. We sort of jumped on that right away. For metals, you should be thinking things in the gigapascals. Okay, when we did calculations with Young modulus, remember everything kind of like 10 to the 9. So that's typical for metal, gigapascals. So 500 kilo, that gets you another like 10 to the 2 right here. This is 10 to the 3, 10 to the 5. You're still well short of 10 to the 9 for giga. And then the mass of an atom, 500 micrograms. How could we maybe bring some form to this with a calculation? How could we sort of disprove that the mass of an atom, 500 micrograms, is not a reasonable estimate? Pick an atom, hydrogen, uranium. That's kind of a good spread there. So hydrogen is sort of the simplest element. uranium. Hey, gives us a nice chance to review some of our radioactivity, right? Nuclide symbols. Let's do uranium 232, let's say. All right, so we've got, that's an atom, but that's an atom too. So it's like, well, maybe we choose something in between, or we calculate with the biggest one and say, well, if the biggest one doesn't even, sort of get us close, or is that too much? Is that too little? Kind of how will we know? Well, the mass comes from the nucleons, right? So hydrogen has 1, uranium has 232. Electrons have mass, okay? And if we consider the added mass of the electrons, which, hey, for the fun of it, let's just add that in there to prove to ourselves again how negligible it is. Okay, let's calculate the mass of a good old uranium 232. So it's going to look like this. We've got 232 unified atomic mass units. Okay, a proton and a neutron have slightly different masses, but they're so close that for the purposes of most calculations, we'll just unify, sort of, kind of average them. And we'll say, okay, well, there's a unified atomic mass. If we scroll up a little bit in a paper 1 or a paper 2 document, you'll find handy little formulae and data. And you can kind of see right here that we have a unified atomic mass unit as 1.66 by 10 to the negative 27 kilograms. Compare that with the mass of a proton, 1.67 by 10 to the minus 27. So the proton is a little bit more, and then we unify it down to this. The mass of an electron you see is given as 9.11 by 10 to the negative 31. So it's like 10, it's almost 10. So it's about 1,840 times less massive. Electrons are about 2,000 times less massive. All right, so let's scroll back down here to question 1. Give ourselves that working back. And we're going to do this calculation right here. So we're going to calculate the mass in kilograms of a uranium atom, which is a pretty big atom. I mean, it's not like the largest, but it's the largest, kind of like naturally occurring one. The transuranic elements, remember, it's like they don't really occur in nature. They're very unstable. They decay. Uranium decays, but it takes like 4 billion years, for its half-life. So 232 times U, and 232 nucleons, right? 92 of them are protons, the rest are neutrons, but together they just unify to be 1.66 by 10 to the minus 27 kilograms. And then once we multiply these, so this is unified atomic mass units, that's kilograms per unified atomic mass unit. So those will cancel, will be kilograms. And then let's go from kilograms to maybe grams. Oh, that's not going to cancel it. Let's go kilograms to grams, right? So cancel out kilograms, go to grams. There is 10 to the 3 grams per kilo, right? So there's 1,000 grams per 1 kilogram. So then we'll be in grams. And then lastly, we can go from grams to micrograms. There are 10 to the 6 micrograms in 1 gram, or you can say there's 10 to the negative 6, grams per microgram. So you put a negative 6 in the denominator, or positive 6. I like to work with positive numbers if I have a choice. So I'd rather put 10 to the positive 6 in the numerator, say that's how many, there's 1 million micrograms per gram. Now we just multiply everything here, divide by 1 a couple of times. I'll take care of that. You guys multiply the numerators, I'll divide by the denominators. We'll meet in the middle. Ready? Go. Done. I've already divided by 1. I just need your answer. So here's how many micrograms I get. If you convert a big atom, okay, and we chose like a really big atom just to say, hey, because I kind of suspected this would be way too much. So even the big atom like uranium has a mass in micrograms of unified atomic mass units cancels, kilograms cancels, grams cancels. I'm in micrograms, and my calculator is showing me 3.85 by 10 to the minus 16 micrograms. Okay, 10 to the minus 16 is anywhere close to 5 by 10 to the 2, right? We're sort of like, that is not 5 by 10 to the 2 micrograms, right? So it's not even close. It's off by so many orders of magnitude. You can clearly say that is not reasonable, right? And the only one that's reasonable is D. But, you know, entertaining the other ones gives us a nice chance to explore some physics, practice some, you know, wave physics there, do a little bit of a, you know, atomic physics, remind ourselves about matter, materials, and typical values for Young modulus. Good stuff.